Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so hi, good morning, and what I'm going to be talking about is network management that we did in the HPC, High Performance Computing Grid, and this would be my contribution to the differential acronyms you have seen here. So it's now essentially what is High Performance Computing Grid, and it's work a service offered by IBM Server Group, and essentially this is a service offered to large customers of IBM. And depending on who you are talking to in marketing, it will be called grid computing, it's called on-demand computing, and a few other words. But essentially what it does is that, like, these big banks and financial companies who need to learn large simulations or stock market things or do financial predictions for a limited amount of time, don't want to set up the full computing infrastructures themselves because they need it once a month, once a year type of things. And so they go and get this kind of rent these cycles from IBM on a hire, and IBM provides these computing cycles to them. There are a small number of sites, like a few, less than 10 sites operated worldwide by IBM, and they are quite popular with people who want to use computing at for kind of like academic grid computing, but except that these are used by financial and commercial customers. Now, in order to do that, I'm just going to show you the logical structure of one of the one of these grids to show what the network system looks like here. And you'll see, basically there are two structures. One is the phase 1 structure and what's called the phase 2 structure. And the phases just refer to the way the grid was planned out, or the data center network was planned out. Phase 1 was the initial offering when the service was rolled out. It was kind of somewhat more basic. We had a VPN service provider. So there was a VPN access box from the service provider, the usual access from high volume Cisco routers with BGP running to provide access, backend by the VPN server, and then we had a VLAN switch. The VLAN switch kind of provided access to a management server or a management servers, and then to a set of server racks. Now with only a VLAN switches, the initial structure had certain scaling limitations. You could only give customers a small number of VLAN servers. So after some time, a year or so of experimentation, the team moved on to a phase 2 design, where essentially instead of just having two replicated access routers, there was a subnet of 4 routers running BGP, and that provided access among them. And we'll see that each of them were redundant with gigabit Ethernets. Then we had 2 tiers of VLAN layer 2 switches, and these two VLANs, these 2 tiers were basically so that each of these tiers could be connected to the other tier and provided multiple redundant paths. Even if one VLAN failed, the other one would provide connectivity. Similarly, each server rack was connected to at least 2 of the front. Actually, it was each of servers were connected to each of the boxes in the front tier, so that you could be connecting to the server through any of the VLAN V2 switches. So a lot of thought had gone into the design of this system to make it easy and efficient to give both resilient service, scalable service, and there were 2 phases that the data center network grew from. Now, what were the requirements? First, when a new customer came on time, the network management staff wanted to provision the network for them very efficiently. They wanted to turn it around as quickly as possible. And the process currently used was effectively very manual. So someone will write in a notepad or Microsoft Word what the customer required. It will get handed over to the network staff who will look at it, figure out what has to be done to each of the switches, and then basically go ahead and provision it. It took a couple of days to do that. Now a few more requirements came in. One is the requirement that in case something happens to the primary grid site, and that something includes things like the failure of power in the northeastern grid, or getting hit by earthquake, or or getting some kind of disaster in one area, you still wanted to provide the assurance to the customer that his site is going to run at another one. So what you needed to be able to do was take the whole customer computing infrastructure, be able to migrate it over to another site. Now the other SP site was planned out with different phases, so its basic structure was somewhat different. But you still wanted the customer things to run. And there was another strategic objective which was put in by the server group, that currently we had a big tiers of servers, and these big tiers of server consume power. And when they consume power, they heat up the data center, and which causes all kind of problems with facilities, maintenance, electric bills, etc. So strategically, the goal was that we would move over, instead of having the rack of servers, we'll move over to the big island with lot of thousands of virtual machines on a single server, so that you could put many customers on it, or when new customers come, you don't add or you don't consume additional power. So the question was, how do we support all these things and make it easy for the network to operate? This was like essentially the kind of summarizing the problem as to what were the input given to the network team. They would essentially get a configuration of compute nodes. So these are the new nodes or the server IP addresses that are given to the customer, and will be told what are the storage nodes, which storage node the customer will get. You have to have access to one or two management nodes, and boot key servers, DHCP servers optionally. So essentially you will get a set of IP addresses, and the network team had to manage and put everything there, which meant managing the VLAN, managing the OSPF servers, and setting up also the server endpoints. Now in the spirit of two researchers, what we did was we went and built a higher level, top level model. We all love to build models and abstractions at the top. Oh. Okay, I'm sorry. Okay, I'm sorry. So I think since I've gotten a time warning, let me go over to the next one. So basically, essentially we first started out at a first level model. We said that, okay, instead of looking at the devices and looking at all the OSPF and the routers, let's build a higher level model of what we call logical connectivity. And I'll go into the details of that logical connectivity. But the basic goal here was the following, that to the customer and even to the management, the guy managing the network, it really shouldn't matter which router is there or whether you are going in phase 1 configuration or the phase 2 customer. Right? You should just be looking at the service that is provided by the network, and the service by the network is essentially connectivity. You are exposing certain IP addresses using certain ports, and there are certain security policies associated with it, certain performance policies, but the performance policies was something we put in because we loved QoS, filters and differentiated services. They were not really used in the HPC grid. And then what we did was put another thing, a layer of templates on top, so that essentially when you are managing this abstraction, you have just got a connectivity abstraction with a few parameters, and the parameters here essentially are the IP addresses of machines that are coming in. So that you are saying that, okay, I've got connectivity to 5 servers running on a certain port. So going into the more details, what did the high level model look like? At a server side, because we also had to span across different grids, there was a notion of 2 different type of managers. One was the endpoint manager, the person who will manage connectivity at the server, and there were 2 abstractions there. One was the application endpoint, other was the connectivity endpoint. The connectivity endpoint was, so the application endpoint was the kind of the port to which you could connect, but it need not necessarily be bound to a current address or port or a physical machine. Now when you actually map it down either to a physical machine or to a virtual machine running on a server, that kind of an application endpoint mapped into a connection endpoint, fully populated with any type of associated addressing information there. The connectivity overlay was the end-to-end abstraction with a few more details. The overlay manager was one who would manage and control the connectivity, open it down, tear it down, and the templates were a way to abstract it and reduce from a few parameters to the detailed connectivity model. Okay, so the connectivity overlay, which was basically our higher level model, was essentially just a few examples that if you really want to run an application export a LDAP server, you will get a connectivity endpoint which is connecting 2 machines, and both the endpoints, which machine is talking to whom. You could, for example, for the bulk of the thing that we run there, we don't know the other endpoint. But sometimes you could specify the other endpoint, like when the customer is coming, we could have the customer coming only for a selected subnet or the range. And we focused on layer 3. Okay. Now, getting into the details of what was the high level model look like, we essentially split the connectivity operation into 5 logical functions. One is what we call splitters, and splitters can be seen as the logical analog of the functionality provided by load balancers. You got multiple nodes, splitters kind of take your connectivity, spreads it across multiple endpoints. Filters kind of put restrictions on who can talk on the system, who cannot talk. Endpoints are things that talk to each other, like servers or clients which will be coming in. Now there is a special type of endpoints which we call entry point, and that was put into the abstraction like that for the data center network. It's just a half of a connection. The other half of the connection, the client is not known. So you put an entry point, and then domains were basically just a collection of endpoints or a simple grouping there. And you connect. So what you could do is that you can take the connectivity and you could essentially draw a graph saying that, okay, at the logical level, my network connectivity consists of an entry point, a few filters, splitters, domains, or a cascade of them. And then from that abstract level of connectivity, you could then map it down to different type of physical topologies. Okay, and in order to make sure that it looked fairly sophisticated, we put in policy which we wrote in XML. And the reason to write it in XML was simply because you had so many tools and editors that you could generate it much more rapidly. And it's like which we went to a connectivity markup language, which is nothing but what we showed in splitters and other things rendered in XML. And then at the bottom we came to these logical operations, and when we put the logical operations, we put them on a web service interface, because eventually we would like to go out and standardize them into appropriate standard bodies, and it looks like everyone wants to standardize on the web services, and then go down to TPM or SIM. TPM is a Tivoli provisioning manager which works with Cisco managers to manage the networks and routers. Okay, so basically if you really look at what we have, the model or connectivity model for HPC grid over here, an entry point with filters and domains, right? And let me just skip through the process of configuration, because that really would be obvious. What you do is you first map the operation to virtual devices, then you map them to the physical resources that are in the topology, and then given that you know the network blueprint, whether it's a phase 1 topology or a phase 2 topology, you could essentially map it to each device configuration, and then you could generate the device configuration, which then gets mapped onto either TPM flows, or what we did for the HPC grid was expect scripts, which will go telnet into the devices and run configuration scripts. So what was the summary? The virtualization at least approach seemed to work for this case. We then took it to a couple of other data centers in IBM for different type of application environments, and so far we haven't found a place where it has broken. Now that is not a formal proof that this is enough to cover all communication, but it seems to be working well in practice. Then we have got what we think is the higher level model or abstraction, which spans what a network connectivity should look like, independent of device, independent of technology, and is basically essentially just on the functionality, the connectivity function that a network provides. Now the lessons learned, of course the configuration helped here. The second, some of the things which we found out was not working well. We thought that, okay, this was such a great function, why confine it to the network? Why not take it to the server and the storage so that you could provision them all automatically? And essentially that's a good idea in theory, but what we soon found out is that the way that services are structured in different enterprises customers, it's really, there are procedural issues which will prevent that from happening. So it's like we have to play and remain in the network space, which is really good for specialized people. Secondly, the phase 1 and phase 2 designs were quite different. So that was something which you cannot assume one single model for doing anything, which was kind of even in this thing was there. But the real the real inflation in our balloon was the following. We were very happy and proud with the top level model, and the generation here. But when we gave it to our SPC grid guys, they said that all that is fine, but you know what? Couldn't you just have written simple expect scripts to automate the whole thing? We really didn't want that high level model. Right? Now on the other hand, like the software group and the product guys, they like the high level model because they believe it can be used in more general situations. So it's kind of a discrepancy between our research mindset of dealing high level models and the management mindset, the network manager is said that, well, forget your high level abstraction and modeling, just give me something that works. The future goal that we'd like to do is that, okay, we just did configuration, but what we'd really like to do is that if say something breaks here, the network admin still has to go down to the Cisco firewall router or the layer 2 switch to figure out what's happening, and we'd like to go to a stage where just from the specification of connectivity overlay, the network administrator just say that, okay, I'm managing it, or the network connectivity overlay is not working, or it has the following attributes. He should not have to look at the detailed device configuration. So if we can go to that goal, then we'd say that, okay, we have been able to build the right abstraction. And I think I'll stop for questions because time is up.
So, so this mapping is sort of generating during the setup time. What happens during the runtime when some switches fail or some devices fail?
Okay.
And which layer of the problem get resolved?
Okay. So in the abstract place where we have like there's a model on top of it which is called the business resiliency model, and that layer essentially says to the network connectivity layer, you have to monitor the status of the following elements and tell us whenever the connectivity gets disrupted. So there are little elements which keep on monitoring the status, availability and uptime of each of the switches and routers, so that when any failure happens which can affect the uptime, then the upper people get notified that, look, your connectivity is disrupted. If the failure happens, it's a two-way redundant switch, one link fails and the other one switches over automatically, then basically that failure is ignored, or the status is changed to be just saying that, okay, it's operating in the last, your reliability has reduced but the operation is still there. But if something happens which disrupts the connectivity, like both the links to the VLAN switch gets broken and the management server can't talk to it, then you get a flag saying that my connectivity overlay is broken, and then the connectivity overlay manager will try to see if there's an alternate path to reroute. If it can, he will reroute. If he can't, then he throws up his hands and sends an alert to the network administrator. So there's a monitoring of the feature, but what we have been able to do is architect for availability monitoring. We have been able to architect for reliability, degree of redundancy, that's in the end-to-end path. Where we haven't been able to do the good job is in diagnostics. If something broke or something is not working all right, what's the root cause of the failure? So that would be something to investigate further.
So is there interaction between the connectivity creation system and the applications themselves? I could imagine that the application might say, oh, I have this hotspot. I'd like the following servers to be clustered close together because they're going to send a lot of data back and forth. Or the networks might say, oh, I'm dragging data all the way across the network. Can you move these two things to be closer together?
Yeah, ideally, in a perfect, that's where we would like to go to. That there's an application manager, a network manager, and they both negotiate with each other, saying that what's the best way configuration. But what is running currently is a static one-time configurator and a bit of monitoring function. So it doesn't do that type of dynamic negotiation yet.
Any notion of the customer's parameters may change over time? The first time provisioning you configure, but later on
Right, no, the customer can change over time, and so basically the operations permitted by the connectivity overlay manager include set it up for the first time or modify it. And when you modify it, you take the current system and try to compute the changes. So the standard operation on the connectivity overlay are create, modify, and destroy. So the standard we'll create to manage the life cycle of any entity.
are you successful in fully automated configuration, or are there things that we need to enter manually?
For the configurations in the data centers, it has been fully automated. Right. again, keep in mind that this is a limited, very structured environment where we know how the connectivity, how the things flow, right? And for any place which is structured and we know how the system has been laid out, full automation is possible. The challenge comes if you go to a ISP network or a very large scale enterprise network with all kind of connectivity and any router and any switch connecting in all kind of weird fashion with any other person. That's where one will run into automation problem. But for the bulk of managed systems where someone has put some thought and insight into creating a kind of semi-hierarchical, semi-structured environment for the network, this type of automation can be done almost completely.